So I welcome once again. So expert of this session is Dr. Rahul Kumar Dubey sir. He is from Bengaluru. They're in Robert Boss innovation kind of companies there. So let me read his credentials and his biography. So I welcome the participants who are there from last session also from 3:30 o'clock. So before starting the session, I wish to read the citation or kind of biography of Rahul sir. Actually, Rahul sir received his PhD, as I already said, from uh, IIT Delhi in Electrical Engineering Department in Power System in 2016. He was a research engineer during 2014 to 16 with the Robert Bosch Corporate Research India, where he was mainly involved in the areas of power system and quality. He was a research and development lead in during the 2016-17 with the ABB Ability Innovation Center, Power Grid, and Grid Automation Unit, India, where he was mainly involved in the areas of power system protection and monitoring. He was a postdoctoral member during 2017 to 2018 with IEPG Group, TU Delft, the Netherlands. He is currently working as an expert in Robert Bosch Corporation Research, India, where he was mainly involved in the areas of research and innovation in AI/ML. His research interest includes artificial intelligence, deep learning, NLP, IoT, and big data applications in vehicle telematics, power system protection, digital signal processing, soft computing, flexible AC transmission systems, wide area monitoring systems also. He is the recipient of the prestigious 2014 Prime Minister's Fellow Award by the Government of India, the 2015 Clayton Griffin Award in Georgia Tech, US, and 2017 POSOC Award for Best PhD Research Work by Power Grid India. He served as a brand ambassador for PM Fellow, CII, SARB India, and PhD. He has supervised PhD and MTech students at IIT Madras and IISc Bangalore also. He is also part of PhD External Examiner and Academic Advisor Board member in many of the universities in India. So this much of rich and excellent record of his academics and research. I welcome once again Dr. Rahul Kumar Dubey sir to present his presentation. So I once again welcome sir, and you can now present, please.
Thank you, Ganesh. Let me share the screen. I think screen is already shared, right?
Yes, it is visible. Yeah.
Yeah. So it's visible, na? Screen?
Yes, it is visible, sir. Clearly visible. There is no problem.
Yeah. So today talk is about vehicle to grid. So unlocking the grid flexibility and revenue stream with vehicle to grid and smart charging. So you know this India story about mobility and revolutions, like number of vehicles, total number of motor vehicles, including cars and bikes and all everything, surpassed the number of household by 6%. So total number of vehicles in India is around 370 millions, and the total number of household is around 350 millions. So 370 million vehicles versus 350 million household. Obviously, this mobility is exploding. So once this mobility is exploding means what? More energy is required for the transport, like fuel and electricity. For EV, like more electricity is required if more EV is produced and all that. And great pressure on the power grid and especially with EV penetrations. So higher emissions unless the clean and smart charging are adopted. Because you know this electrical vehicle is manufactured and all this manufacturing industries use this coal-based electricity and all. So still we are not achieved this more penetration of renewable energies and all. So the source of energy is still the coal-based energy. So that's why we don't have the clean energy still. So when you have a large number of motor vehicles versus a household, obviously it require a fuel and electricity for the transport and all. So you require more energies and all. So a sharp need of sustainable mobility systems such as EV adoption and vehicle to grid, renewable energy integrations and intelligent energy management is very important. Now you see this electrical vehicle we see as only the energy consumption, like it can take the energies, it can't supply the energies. Okay, so vehicle to grid technology means can we do reverse also, like can electrical vehicle act as an energy source and all. So that we are going to discuss and all, and how this energy management is going to work and all. So where does this energy stress actually comes from in the ecosystems? So this is the first questions we need to ask ourselves. So where does this energy stress actually comes from in the ecosystem? So if you see the current ecosystem of e-mobility, there is a three individual pillars. So the first pillar is electrical vehicles. The second pillar is about energy infrastructure like generation, transmission, and distributions. And the third pillar is charging infrastructure. So if you see the three pillars, they are isolated. They are not interconnected or interoperated and all that. So electrical vehicle, if you see individually, we are focusing more towards the vehicle-centric innovations. Like if you see the electrical vehicle, we are mainly focusing on the battery side, mainly the lithium-ion battery side, like how we can do this battery aging impact and all. And then motor side, these are the two component, like vehicle centric innovations we are focusing on. Similarly, energy infrastructures, the overarching grid and system, energy generation and distributions and all. So mainly like generation, transmission, and distributions. So these three pillars are not interlinked to each other, so they are isolated. So how this integration? So integration is the key to e-mobility for potential. So how we are going to integrate it so that all three should be like intelligent, interoperated, and integrated. So the current ecosystem, the challenge, as we discussed, like EV limitations, like one-way energy flow is only happen, like limited to grid support. So generally, currently, if you see, electrical vehicle is only used for the charging. It is not like you can't do reverse, like bidirectional charging, like vehicle to grid. You can't do that. So that kind of robustness is not there. Like grid is not supporting that kind of robustness and all. So how we can make our current grid so robust that so whenever the time is required during the peak time and all, so electrical vehicle is also act as a one source apart from the renewable energies. So similarly, if you see the grid side, it is an unstable power management, load balancing issues are there. Similarly, you see the charging infrastructure side is a vendor specific solutions. Like there is no communication between the system, like they are not communicating with each other and all. So basically the integration is the key to unlocking the full potential of e-mobility. So if the pillars are fragmented, the question you ask, if the pillars are fragmented, the natural next question is what does true e-mobility vision look like? If you see the fragmented pillar, like all these three individual pillars, like electrical vehicle and then energy infrastructures, like generation, transmission, and distribution, and then charging infrastructure. So these are the fragmented. So this act as isolated today. So how we can make the three eyes like unified ecosystems? Three eyes means the first eye should be intelligent, second eye should be interoperable, and then integrated. So once we do this unified ecosystem, then the vision of true e-mobility can be achieved. So intelligent, what does it mean by the intelligent? Intelligent means the system that optimize the energy use dynamically, respond the real-time conditions and user needs. So based on the condition, it can be adopt the situation and that energy demand can be fulfilled. So similarly, interoperable, you see the component that communicate seamlessly, like components should be talk to each other, like communicate from one party to other party. Like EV can communicate with the energy infrastructure can communicate with charging infrastructure. So vice versa. So that should be interoperable to each other and then integrated. The holistic approach connecting all aspects of e-mobility landscape for unified operations. So these three are the key, like intelligent, interoperable, and integrated. So these three eyes unified ecosystem we need for true e-mobility visions. So right now it is a individual pillars. So three pillars are individually, like electrical vehicle is a individually, like there we are focusing on the vehicle centric innovations. Then energy infrastructure also, you know that generation, transmission and distribution, that is separate issue. Like there we are focusing on IBR and then power quality issue and then a lot of other challenges we are focusing. So similarly, charging infrastructure is a vendor specific and all that. So how we can make this unified ecosystem with three I's, like intelligent, interoperable, and integrated. So that once we implement these three I's, then our grid should be more robust and then energy demand also can be fulfilled. So unified energy architecture, once you look for this powered by three I's, like all this solar PV, battery storage, and smart meter, inverter, electrical vehicle, and utility grid. So all should be interconnected to each others and all that. It should be intelligent, interoperable, and then integrated. So these three I's, so all these three I's should be present in all these three renewable sources like solar PV or wind sources or battery storage, smart meter, electrical vehicle, utility grid, and inverter and all. So all should be integrated to each others, and then it should be intelligent, and then it should be interoperable. So this is the vision for unified energy architecture. So integration enables the intelligent energy management across the board. So with this architecture in mind, the next building block is smart charging. How are actually control power flows? So once you vision for true e-mobility and unified energy architectures and all, obviously then the next question is smart charging, how we actually control the power flow. So what is smart charging? So smart charging is a series of intelligent functionality to control the EV charging in order to create the flexible, sustainable, low cost and efficient charging environment. So mainly the flexible is responsible for adapt to charging and energy demand. So when we are going to charge our EVs and all, and then it should be sustainable, like optimize the renewable energy sources, like when the wind and the solar's penetration is high, so that time we can charge our vehicles and maybe the cost will be less that time. Then it should be cost effective, reduce the charging expenses, and then efficient, the maximum grid utilization. Though we should utilize the maximum grid. So this individual component we will discuss in the later slide. So we will see how this works and all. So benefit of smart charging is like increase the flexibility, high utilization rate, then efficient energy distribution and enhance sustainability and new revenue streams and all. So these are the benefits for smart charging. So smart charging is a foundation. On the top of that, V2X technology extend this to full bidirectional power and grid services. So we understand what is smart charging, like how we are managing and controlling the powers and all. So now we are going to understand what is V2X technology and all. So if you see the right side, so completely V2X technology, you can see like from unidirectional power flow to bidirectional power flow. Unidirectional power flow means suppose you have a electrical vehicle and like currently you have electrical vehicle and you are charging your electrical. So electrical vehicle is only act as a sink. So it is only taking the energy. It is not giving back. So that's why it is a unidirectional power flow. V1 to G. The use cases would be like a smart charging app, time of day tariff, and renewable aligned charging, like solar charging and all. That is a example for unidirectional power flow. Similarly, if you see the second part, like bidirectional power flow, like bidirectional power flow means you are taking the energy from the grid, and then whenever it is required, then you are supplying the energy to the grid. So that is a bidirectional power flow. So means the use case mainly like send power back to the grid, then grid balancing during the high demand and renewable integrations and all. Similarly, the next component should be like vehicle to home instead of vehicle to grid, vehicle to home, and then vehicle to building, and then vehicle to everything. So if you see the vehicle to home, EV battery powers home appliance like during power cut and peak tariff hours, solar shortfalls and all. use cases may be like backup power. It can act as a backup power and household energy optimization. Emergency time, during emergency time also it can be helpful. So similarly, if you see the vehicle to building is also like same, it is peak demand saving, energy cost reductions, backup power for critical loads, like a lot of commercial building. If you see commercial building and malls and take park, so there is a parking allotment is there now. So there is a lot of maybe one EV is not able to contribute a lot of energies, but multiple EV if you see, they can contribute, right? So parking lot is a in the smart building campus, like in Bangalore also we have a tech park and all, right? So there it can be useful, or maybe mall also it can be useful, where you have a parking slot and charging is available. So similarly, if you see the vehicle to vehicle, so like one vehicle can charge to other vehicles also. Like one example is like you can use this laptop. Na laptop you can use for mobile charging, right? You can connect the wire in the laptop and then you can charge your mobile. So similarly, you can charge from one EV to other EV also, right? So that is nothing but vehicle to vehicle. So it may be helpful for the roadside assistance. For example, EV is not petrol car, right? Suppose if you have started your journey from your home and then you reach and midway the battery is gone, and then obviously you don't find some petrol pump like EV charging station, right? So there maybe this EV, other EV can be helpful, because EV act as a mobile energy, right? Mobile energy means it can move from point A to point B, right? So it is a movable asset. So one EV can charge to other EVs. So that is nothing but V2V technology. So it will be like use case like roadside assistance and then fleet to fleet energy balancing and all. And then the sixth one is a V2X, where V2 everything will be like umbrella term is coming covering like vehicle to grid and then vehicle to home and then vehicle to building, vehicle to vehicle. So this interaction includes all this in smart grid, microgrid, renewable plants, energy market. The use case like grid services, home backup, like you can use your EVs for your like emergency power supply in the home and all, right? So that can be it can be useful. So always remember that whenever you are using EV as a power backup and all, only you can use 10 to 20% of depth of discharge. Understand? 10 to 20% depth of discharge means your SOC should not below like 70 to 80%. So 10 to 20% is a safer margin where it will not impact your battery aging, because battery, lithium ion battery is this electrolysis and all this chemistry will be impacted, and that will impact your battery agings and all. So always remember to use only depth of discharge up to 10 to 20%. So here you can see the tables like battery size and category and all. So for example, if you are considering these small EVs, maybe Tata Tiago or EV LR, where this small EVs is having a capacity of 20 to 30 kilowatt hours. So if you consider this second column like usable V2G, 10 to 20% depth of discharge is, if you consider 20 kilowatt hours, 10% is 2 kilowatt hours, right? And then 20% if you consider, then is around 5 to 6 kilowatt hours. So that can be useful for home loads, and then like lights, router, fan, small fridge and all, that can be up to 1 to 2 hours it can be useful. This is a small EV segment. Mid-size EV segment, like where the this capacity of battery around 40 to 60 kilowatt hours. The usable V2G, like depth of discharge is 4 to 12 kilowatt hours. So it is very good for residential V2G. So like MGZS EV is the examples, and then it can be used for this export 5 to 8 kilowatt or between 6 to 9 PM, reduce the household bill and to support the local filter. So in the night time, if you see some cities, it can be useful. And then if you see the upper mid or premium EV segment, where this battery capacity is more like 70 to 90 kilowatt hours. The usable V2G like 10 to 20% is 7 to 80 kilowatt hours. Like Tesla is one example and all. Volvo EX30 is also having this kind of capacity. So this can be useful for provide the frequency regulations, plus absorb the midday PV surplus and discharge in evening while still keeping long daily driving range. So you can use up to 10 to 20% of depth of discharge. Similarly, if you see the larger segment like SUV and trucks, buses, like the capacity is around 100 kilowatt hours, and then usable like you can use up to 10 to 25 kilowatt hours. So it is a strong participation in flexible market and all. Like Ford is the Ford F-150 will be used for lightning and all. So supply a small building depot with 10 to 20 kilowatt during evening peaks, provide the high power reserve and grid services. So you can see from the small EV segment to the larger EV segment, from 20 kilowatt hours and up to 100 kilowatt hours, it can be used for different purposes and all. But in each case, you remember that you should only use up to 10 to 20% of depth of discharge, because beyond that, if you use, then it will be impact your battery agings and all. Okay, so up to 10 to 20%, it is flexible. So it is not going to impact your battery agings and all. So V2X power is a powerful, but it is not free. Okay. So there are technical and operational challenges we must address. So what are the technical and operational challenges we must address? So what are the advantage of V2X? So advantage is like, as we discussed, like it can act as a storage for renewables and all, like buffer the intermittent renewable energy sources. Then the reduced peak demand, like lower the grid stress during the high demand periods and all. Then it can act as an emergency power, like as we discussed, like it can be work for the backup powers and all. Then it also act as an ancillary service, support the grid stability and frequency regulations. So you know this one single EV maybe is not provide too much support to the power grid, right? But if there is a large scales of EV will be used, then obviously it can be it will be useful for the B2G technology like bidirectional chargers and all. So what are the challenges? These are the advantages. Left side is the advantage and the right side is the challenges. So challenges is obviously the bidirectional charger. So require a specialized equipment and all, obviously. And then battery degradation is one of the challenges. Additional charging cycle may reduce the battery life. So as we discussed, when we are talking about V2X or V2G or V2 home or V2 building or V2V, so we always remember that we should not go beyond depth of discharge up to 10 to 20%. So if you are going beyond that, then obviously you are playing with the aging of the batteries and all. So that's why the battery degradation is one of the challenges. So always play smart, like keep up to 10 to 20% of depth of discharge of the battery. So it will not impact your battery agings and warranty and all that. Then the third one is the ICT infrastructure, like complex communication system needed. Obviously, you need a for this intelligent, integrate, and then interoperable. Obviously, you need a infrastructure, ICT, and all that. Then obviously you need a standardization and regular framework is still developing, like CEA and then other government authorities already working like DESCOM and all that. And then user incentive, lack of compelling benefit for EV on Arata. So for India, you see this is a very modern technology and people are still working and all. But if you see other developed country, it is already in work. Okay. So V2X charging infrastructure, if you discuss, so there is a two kind of charging is there. Like one is AC charging and one is DC charging. So once we talk about the AC charging, so AC charging is nothing but bidirectional onboard EV charging integrated within the vehicles. And DC charging is a bidirectional offboard EV charger located at the charging stations. So when we talk about the AC charging means your this onboard charger OBC is already inside the vehicle. Okay, so means inverter is inside the vehicle. So you are receiving the AC and then inverter is converting the DC and then it will supply back to the battery. But when we talk about the DC charging or fast charging, DC charging is also known as the fast charging. Okay. So once we talk about the fast charging means inverter is outside the vehicle. Okay, because here you are directly getting the DC. But in AC charger, inverter is inside the vehicle. So it is an onboard charger. So here is the game, like people are working in this direction, onboard chargers, how we can make it more impactful and all that. So there is a two kind of charger is there, AC charging and the DC charging. So only difference is in case of AC charging, you have an inverter inside the vehicle. For DC charging, you have an inverter outside that charging station. So you are getting directly the DC, okay. And obviously when you are doing the AC charging, the charging time is high, okay, because your kilowatt hours is less. When you are doing the DC charging or fast charging, your charging time will be less, okay. So these are the fundamental things. Somebody asks, then you should be able to answer this. So with fundamentals clear, we now see how smart charging actually behaves in a real system. Load balancing, renewable, price, peak, and backup. So we are going to discuss about this charging strategy and how we are doing smart charging controllers and all this. So this application of smart charging is the first one is a local load balancing. The second one is a renewable energy utilization. Then price-based charging, peak saving, and the grid backup. So we will go one by one. So first we will focus on the local load balancing, where we are focusing on the adjust charging time and power according to the load balance multiple charging point with priority. So if you see the load balancing in action, so if you see this orange line is your load power. Y-axis is the amount of energy and then x-axis is the time. So if you see this load power versus the smart charging power. So when the load power is less, when the load is less, then smart charging is high. When the load is high, then smart charging is less. When the load is very high, then smart charging is still stop. So EV charging reduces during high load and increases during the low load grid to support the grid stability. So when the load is less in the grid, so obviously you can take a charge. You are using a smart charging, like you can charge that time. When the load is very high, means high peak demand is there, so you should reduce smart charging is reduced, like it is not using that charging purpose and all. So similarly, if it is very high, then you see smart charging is put on. So second, if you see this, there's a multiple cars are there. So there's a charging strategy, like if you see the first block where the sequential charge, like car is charged one after the another, like first car 1, then car 2, and then car 3. If you see the second pictures, it is a parallel charging. All cars charge together. It is a parallel charging. Multiple cars share available powers. Then if you see this, the third one, it is a load aware charging. Like based on the load, like car 1, car 2, and car 3 will be charged. So this is a smart charging behavior. So based on the energy availables and all, so that kind of strategy it will be automatically can be built, or optimization can be built, optimization model for charging. The next you see the renewable energy integrations. Like if you see the x-axis the time and the y-axis is your amount of energies. So if you see this wind penetration is high, your charging will be high. During a midday, when the solar is also the solar power generation, the red one, if you see the mid of the day, it is high, and then your wind power is also available. So both the renewable sources is available. So smart charging power is high. So when it is going both is down, you see the smart charging is going down. So wind power generation is charging when wind energy is abundant. Solar power generation is optimize the charging during peak solar hours, and then smart charging power adapt to renewable availability and all. So based on the renewable energy availability and all, here you can see both wind and both solars during mid of the day. Solar is also is in the good amount of energy is giving, and then your wind is also available here. Here you see the smart charging power is high. So starting of the day, if you see only wind power is there, but the solar is not there too much. Here you see the smart charging is following the pattern of the renewables like wind sources and all. So when both renewable sources is available, and it is at the peak. So similarly, the third one is the price-based charging, smart charging. So you see this blue dotted line is a smart charging power, and then this line is the electricity price. So if you see the electricity price when the tariff is less, then smart charging is high. When the tariff is very high, price is very high, that time we are not charging it. So user is getting benefit. Okay. The second figure, if you see the price level is fixed by the DESCOM or some other players. Suppose this per unit the price is fixed. This pink line is the fixed price threshold is there. So if you see this electricity price curve, when the electricity price is less, then that time you see the smart charging is a maximum. When the electricity price mid of the day is high, you see this smart charging is negative. Negative means what? So it is not charging. It is not taking a charge. It is supplying the charge. Understand? Like it is a reverse, like vehicle to grid. Understand? So during when the price is high, and if you have a storage, for example, your EV is 100% SOC, that time when the price is very high, when that time if you supply this energy back to the grid and all, then you can earn the money, right? During this period, from this point to this point, you are supplying when the price is very high. So you can earn some kind of money, understand? So again, when the price is going below the threshold, this pricing level below go the threshold, then again you are charging. So understand. So when the price is less, that time you are charging. When the price is high, that time you are supplying the energy and you are earning the money. So this is the price-based smart charging. Then the fourth one is a peak saving strategy. So if you see this red one is your solar power generation. Mid of the day it is very high, and the load power is also, you see the curve. So when the solar power is high, so that time you are charging your vehicles. Understand? But when the solar power is go down, you don't have any renewable support and all, and your load is high, that time you see the vehicle is supplying the power back. Means again you are earning some money here. Understand? So again when the load is less, then again it will be you are going to charge. So obviously the strategy is when the price is less, that time you are charging your vehicle. When the price is high or demand is high, that time you are supplying back so that you can earn some kind of revenue. Understand? So this is the peak saving strategy. Similarly, the fifth one is a grid backup capability and all. So if you see the green curve is your wind power generations. Y-axis is the amount of energy and the x-axis is the time. So wind power, you see this green one is the wind power generations, and load power you see load power is here it is moving from this point to this point, and then the grid power you see. So you see that when the wind power goes down and your load power is still increasing, so you don't have any renewable penetration and all, and your load power is increasing, then grid after some point here the grid is failure is happened. So during this point we are going to supply back the energy to the grid through vehicle to grid technology. So grid failure backup from EV to V to G. So once your load is less and grid is recovered, then we will take out the support. Understand? So that way it can act as a backup protection. It can be act as a protection, like it fulfill the energy demand for the grid and all. So normal operation is like wind power generation and the load power is balanced. The second one is the grid failures. Grid power drops and triggering the backup mode. So grid power here is dropping and then here triggering the backup mode. Then EV backup vehicles discharge to support the critical load by V2G, that bidirectional charges and all. Then once the grid recovery, like normal operation resumes from this point, once the normal operation is resumed, when the load is less and normal operation is resumed, the EV return to the charge. Understand now? So basically the strategy is, so one is a price-based strategy. When the price is high, that time you are supplying the energy to the grid. When the price is less, that time you are charging your EV. So when the load is high to the grid, when there is no renewable support, then it can as a backup source. EV can act as a backup source. So this is overall applications for smart charging and all. So these mechanisms are not just theoretical, they are already being used worldwide. So what we have discussed in theory, so we are going to see where this technology is useful and where currently it is used in world. So real world smart charging application, if you see the Tesla like supercharging network, the supercharger network dynamically manages the power distribution and thousands of vehicles, prioritizing the charging speed and balancing grid load and minimizing the infrastructure strain and all. So whatever these curves we have discussed now, so you understand this how Tesla supercharging network is working. So similarly, this workplace charging program is also there, like big campuses. If you see the Google, Siemens, it is not in India, but right now in US, they are using in US and Europe. They are using mainly Google, Siemens for smart building and all these campuses. They are using this technology V2X. Then apartment building installations and all, like urban residential complexes, as we discussed, like we can use for like commercial places or mall or smart campus or tech campuses, where or metro station also one example, like metro station, lot of vehicle park, no? So not one vehicle, so lot of vehicle is parking and lot of charging station is there. So there also it can be act as a vehicle to technology, vehicle to grid technology is very helpful. Then fleet management system is also if you see this Amazon and United Parcel Services and all. So this is they are using this technology and all, like fleet management systems and all. Then V2X in practice and global pilot projects. So some of the pilot is already working, like Nissan. You know that Nissan vehicles V2G trials in the Denmark, they have done already. And then Japan also, they have done like plug-in hybrid vehicles is a key player in vehicle to home. Like for home, they are providing this backup power for home during the outages and all. So, and also we have discussed about this Ford F-150 Lightning USA and all. Like the Ford 150 Lightning offers the intelligent backup powers, enabling the truck to power a typical home up to 3 days. Like up to 3 days, they can provide the backup power, because the battery capacity is high, and if you take the 10 to 20% of depth of discharge, so obviously you can make it up to 2 to 3 days. An European V2G project, like across Europe, numerous V2G initiatives and underway often. So a lot of people are working in V2G technology in India also. People are exploring, and then because we need a infrastructure support for this and government support, regulatory support, a lot of support is required to make this technology work in the ground. Because in other country, if you see, it is not like India. So once you are doing some small thing also, you need a lot of approvals, right? So India obviously implementing this, and it will take time. So by 2030 or maybe next 10 years, we can see this visibility of this technology and all. But other countries is already implemented and people are working on this. So from this pilot, we can quantify the real impact in terms of money, reliability, and sustainability. So we have seen that how this electrical vehicle is not only act as a sink, like it is not only energy consumption, it should be energy supply also. It can be supply and it can be act as a one kind of, you can generate the money and all. Like suppose during the peak hours or when the tariff is high, that time you supply back the energy and you can earn some kind of money. And when the tariff is less and load is less, and that time you are going to charge, so you are charging at less cost and you are supplying at the high cost. So obviously you are making money, and obviously your battery is also not going to impact because you are using depth of discharge up to 10 to 20% only. So your battery aging is not going to impact it. So the practical benefit and real world impact, like obviously we discussed like cost saving for EV owners and all. So participant in V2G programs can earn up to. So these are the numbers you can. It vary based on the scale of the EV, how many EVs uh, you are using for this for vehicle to grid technologies and all. Then enhance the grid stability. Obviously, it is going to support and make the grid more robust and all. So one EV is not going to make your power grid robust, but if you take the scale like multiple EVs, like for example 30% EV penetration is if happens in India by 2030, then it is obviously the large number, right? So that can be useful for this making the grid more robust. And then optimize the renewable integration and energy power backups and all, like Ford and all, they are doing that. So now let's connect this back to integrated platform using an India relevant ecosystem examples. So you heard about this unified mobility platform. So one example is the Geo. Geo is doing that, and then Geo Energia is the platform name, where this smart EV charging and advanced vehicle telematics, smart digital clusters, smart battery management, smart fleet management, energy management, all these three are there in the common platforms. So basically, this smart EV charging is nothing but the intelligent management of charging process based on the real-time grid conditions. Then advanced vehicle telematics, where telemetry data is there, like you can see the inside of your EVs, like locations and all that. Yeah, because you will get all the sensor, telematic sensor data, real-time data, and insight of vehicle performance and usage pattern, driving behavior that you can see. Then smart digital cluster, like user interface control system within a vehicle and enhanced experience and all. And then smart battery management like BMS and all that, optimization of battery health, like state of health and all that, performance and longevity of fleet. Then smart fleet management, like fleet, you understand, like multiple vehicles you can track there. So solution tailored for commercial EV fleet and optimizing operation and cost, like Mahindra and Tata vehicles we are doing currently. Boss is doing for Mahindra and Tata. And then energy management platform like True Powers and Geo Energia for broader energy optimizations and all. So this is a unified mobility platforms. So where this intelligent, interoperable, integrated, these three I's mainly going to focus. So integration is the key to unlocking the full potential of e-mobility. The true, the future of this future of sustainable mobility is like where EV as a act as an energy provider. It is not only like take as an energy sink. Like it should be not like only take the energy from the grid. It should supply also energy back to the grid. Maybe like vehicle to grid or vehicle to home or vehicle to building or vehicle to vehicle. So that is a one part, like EV as an energy provider. So where you can earn some kind of money. Then smart charging is one component of true e-mobility, and then smart grid. Smart grid means like is a combination of all this ICT and all power system, power electronics, and all this, and then renewable energies and all. So these are the four important components for true e-mobilities and all. And EVs transform from energy consumer to active participant, creating the sustainable transportation ecosystems. So as we discussed, like it should be not only act as an energy sinker. It should not only take the energy, it should provide back to the energy also. And then intelligent integration optimize energy flow, and then ensuring the efficient use of existing infrastructure. Economic benefit emerge for EV owners. So EV owners should earn some money also through this energy management or smart charging tools. So this is the one important benefit, economic benefit, that you can't do it in your petrol vehicles and all. The future of mobility is intelligent, integrated, and sustainable. The future of mobility is intelligent, integrated, and sustainable. So thank you. So I will discuss one this real platform also once. Let me show how it works. So for example, you see, this is, you are able to see my screen, right, Ganesh?
Yeah, yes, sir. It is visible clearly.
For example, this is the EV smart charging controller. So this is one campus, as I discussed, na, like tech campus, where 35,000 employees are there, corporate campus is there. So here, for example, we have analyzed for 30 days, total 27,000 sessions, 900 sessions per day, and total number of vehicle is 13%. Understand? So 13% of 35,000 is around 4,500, right? And total here EV users has 90 AC charger. AC charger, we understand, na, this where this inverter is inside the vehicle, onboard charger, okay, onboard charger, bidirectional charger. And there is a 10 DC charger, fast charger, where inverter is outside the charger.
Side
So
charger.
this is the data set we have observed. And then this is the number, like total number of days, 1 month we have observed, total sessions, average session per day, unmanaged peaked, minimum, and then average and all that. So for example, if you see this summary of 30 days, so you see this is the unmanaged peaked. This blue line is the unmanaged peaked, and this orange line is your optimized peak. So this is the threshold of up to 500 kilowatt. So this optimize is always be less than your this threshold. So daily energy cost before and after, you see the energy cost before the optimization and after the optimized cost. And comfort level across day, this state of charge requirement met. If you see the 60 to 70% of the vehicle met their SOCs. And these EV vehicles are the combination of two-wheelers and this four-wheelers, okay. And four-wheeler also is having a combination of first generation and second generation. So this is a month-wise summary, 30-day summary. So for example, if you selected day, if you say, suppose you see the selected days, this is the 1 month data. If you see selected day, you can select any days. So for example, if you are looking for this 5th of January 2025 data, so here you see the matrix, and this is a KPI. So where the feeder peak reduction is up to 65%, cost reduction is up to 32.3%, and comfort SOC met is 88.4%. Means total number of vehicles,
तो इसमें पता नहीं कैसे नहीं चल रहा है
88% has met their SOC, okay, and then 793 session is happens. So here you can see this curve. X-axis is the time and day, and then the power. So here you see the unmanaged EV. So where you are not applying smart charging and all. So when you are applying smart charging, is this blue one, you see the optimize, this came through the linear programming and all. So it is always below this feeder cap and all, okay. So here you can see, if you see this demand response, if you enable this, then it will go up. So if you just enable this, then it will go down, you see. But it is always below this threshold, the grid threshold. And you see here the shortfall by vehicle types also. So E two-wheelers, then E car first generation. First generation means there is V2G is not, bidirectional charger is not available, okay. So it only act as a sync. Second generation, where we can bidirectional charger are there. So if you see the two-wheelers, zero, like means two-wheeler maximum vehicle has been charged, all the vehicle has been charged, because you know that two-wheeler, the charging this kilowatt hours requirement is less. So obviously it is the first priority, and it is all the two-wheelers is getting charging, to bike and all. Then the second one is the first generation or second generation. You see up to 60, around 60, 40 to 60% second generation and first generation is also going to charge. So this is a performance by contract types. So total energy delivered per contract. You see the employees is having the first priority. The employee, all the vehicle is charged. Then the second premium and then the visitor and all. Visitor is having given the less priority. Once employee has been fulfilled and all, then visitor can be done. These are the KPIs, and then you can see also, so both, so linear, you understand this linear programming and then this model predictive control and all. So in linear programming, what we do actually, we day ahead energy requirement and that we are going to forecast. But in MPC, in every 15 minutes, you can forecast because you don't know when the EV is going to arrive and when it is going to, like, it can arrive early also, right? So this MPC, like model predictive control, is mainly for the real-time purpose. It can be useful because you don't know when this EV is coming for charging and when it will be leave and all. So generally in the real world or in industry, we use this MPC, and then IMLP also, like integrated multilinear programmings and all. So you see when I click this, so it is running in the cloud. So that's why you are seeing here the running. So once it is, you see that it is, here you see the outcome. So this is unmanaged EV load when without smart charging. Then the orange one is optimized linear programming. This is orange one, optimized linear programming. And then optimized MPC, optimized model predictive control. And then this dotted line is the EV feeder cap and demand response up to 500 kilowatt. So it is a small, this smart campus, or where this feeder capacity is up to 500 kilowatt. But when you are talking about one city, suppose you want to do for one city, then for India Descom, this limit should be up to megawatt levels. Okay, up to 1 megawatt to 1.8 megawatt. So here you can see this MPC, the green one is providing better support compared to this optimized LP, because in every 15 minutes it is updating. So that's why it is near to that grid. So, and this is the headroom. So headroom means this headroom can be useful for the vehicle to grid purpose. So here you can see the distribution, like two-wheelers and first generation and second generation. And again, here you see the employee, those employee vehicle has given the first priority, and then premium, and then visitor. Okay, so this way, it is one example how it is working and all. So thank you, Ganesh and team, for
Yes, yes.
organizing this talk.
Okay,
So
sir.
from
Wonderful
my
session.
side,
Yes, sir.
it is done.
Okay, all right, sir. Thank you. Thank you very much for the wonderful session. It was really wonderful and very much informative. So we have also learned about the how an smart charging works. This was really very much interesting. That we can even earn with the help of our EV electric vehicles, which we are having. So as
So
you said,
I
sir.
hope I have not taken, much time.
No, no, it's all right, sir.
So
No problem. It's great actually. So actually, this is very much interesting that if anyone having EV can even earn by just injecting the power when there is the high price of tariff or high tariff rate is there, isn't it, sir? It was
yeah.
really very much interesting. So, so very, maybe some, many of the people who are there in
So
the participants list may
maybe
have their own EV, and if the smart charging works in our country, then definitely they will also be earn something out of their electric vehicles also.
no, no,
Sir, you are not audible. Are you are you there, sir? You have been muted yourself, maybe, or you have left.
this
Yes, yes.
grid.
Sir, are you there? Actually, we are not able
So
to.
thank you, Ganesh.
Yes, yes, sir. So I think you may be having one another assignment. So thank you, sir.
Yeah,
Thank
so
you very
thank
much
you.
for
If you have
speaking.
any further question, you can ask. Yeah,
Yes,
if
yes.
you have any further question, you can ask, or you can write to my mail. Somebody, if you want, write to
Okay.
my mail. And those who are interested to working in this area, those faculty, those who are working in the interested to work in this area, for example, research they wanted to work in some research problem or some research paper or something like that, they can also contact me. So I have some good problem statements and all there they can work on, and what that problem statement, like maybe that is smart charging or bidirectional charging and all, or
Yes.
maybe like aggregator side also, or some other maybe in the battery aging side also, like second life of battery. So there's battery aging like below 80%, so battery can be useful for other purposes also.
Yes.
Understand? So how you're going to measure that and all that, you can make some kind of money and all that apart from you
Yes, sir.
can do some kind of consultancy and also this is a growing technology and all, people should work on this. So India needs this actually. India Smart Grid Forum also needs this.
So
Thank you.
is this kind of mechanism is there in India, sir? Is it anywhere in India somewhere?
So yeah, right now, like you see the vehicle to home and all is there, like vehicle
Okay.
to home or vehicle to for light charging and backup, you can use that. But grid and all, still it is on the work, because grid, that grid is not, still it is not bidirectional and all. We need a lot of regulatory support and all that, right?
Yes, yes.
Suppose you build a technology also, then obviously you need some regulatory work and all that, no?
Yes, yes,
And
exactly.
then
It is
and
something.
also,
Yes.
yesterday I was discussing with some CE guy, like they are also working on dynamic tariff. Dynamic tariff, understand, no? Like right now it is a tariff of electricity is a fixed tariff, right?
Yes, constant.
Based on the states and all, right? So once this technology will be introduced, means we can introduce this dynamic tariff. So based on the renewable penetration, availability and all that, tariff will be going to change and all that. You can, that time you are able to, if you have a lot, if you have 100% of SOC and SOH, then that time you can supply back the energy at the high rate and you can earn some money. And always remember, like you have to maintain up to 10 to 20% of the depth of the discharge, because if you go for beyond that driving cycles and all, then it will impact your battery aging, so your warranty and all will be impacted.
Yes.
So if you go in this range of 10 to 20%, then battery is healthy, and the state of health of the battery is not going to impact, and you will earn some money, and that money you can maybe useful for some other purposes.
Yes, yes, exactly.
Okay, so thank you.
So, okay, thank you, Rahul sir. Thank you very much for sparing the time with us. Actually, this was really wonderful session and quite generalized. Every people who are there in the meeting have enjoyed, I hope. So, on behalf of our organizing committee or from our institution, Engineering College Bikaner, Bikaner Technical University, we again thank you for sparing time with us and having this session. So thank you, sir. Now you can leave. Actually, the other document
Please
purpose
give
and
me
other
your
thing
email
I'll
ID
call you
and
later
mobile
on.
number.
Is
Sir,
there anyone
please
wish
give
to ask
your
something?
mobile number.
Okay, okay, okay. You can contact me or you can send me any personal chat message on that WhatsApp group. I am available there, so you can send me there.
Okay, sir. Thank you.
Okay, Rahul sir,
Thank you, sir.
thank you very much. Actually, we have another session which is there after this, and this is about the validity session. So it's about 6:30, and we will start the next session that is about the validity. Although we will only have the feedback from the participant side if they have in the next session that is on validity. So that is also mandatory session and that need to be attended by every participant. So please be here only, and we will have just after 4 5 minutes. So Rahul sir, thank you very much.
Okay, so I can leave now, right, Ganesh?
Yes sir, yes sir, yeah sir, exactly.
Yeah.
Thank you very
Thank
much
you
once
very
again.
much. Okay.
Okay.
Yeah.